Hello, everyone. Welcome to the London Machine Learning Meetup. I'm Giuseppe from Evolution AI, and I'll be hosting today's session. So today we have Anis Kazi from the camp at the Technical University of Munich. And she's going to talk to us about the graph convolutional network for disease prediction with imbalanced data and multimodal data analysis. The talk is going to be moderated by Fabrizio Frasca, who's a machine learning researcher at Twitter Cortex. So as usual, the talk is going to last between 30 and 40 minutes, and it's going to be followed by a Q&A session. Please do ask questions in the Q&A tool at the bottom. We will answer all the questions at the end of the talk. If you have any technical issues, please use the chat to speak to us. And as usual, the talk is going to be recorded and it's going to be uploaded onto a YouTube channel. So without further ado, I'll leave the stage to Anis. Thank you.
Thank you so much for the introduction. Hello, everyone, and welcome to my talk today. So the subfield that I work in is graph deep learning for healthcare applications, but today we will be focusing on graph convolutional network for disease prediction with imbalanced data and multimodal data analysis. So basically two of the paper of one of my PhD students. I'm Dr. Anis Kazi. I'm a senior postdoc at Computer Aided Medical Procedure and Augmented Reality Chair at Technical University of Munich. So before we dive into the topic, I will just give a brief introduction about myself as well. Okay. So I did my master's from Indian Institute of Technology, Kharagpur, with a major of medical imaging and informatics. And I came to Germany with a DAR Master Sandwich scholarship to do my thesis at camp itself. And my thesis topic was cross-modal manifold alignment for cross-modal image retrieval. I started my PhD at camp in 2016, focusing on deep learning for medical applications. I focused on bone fracture prediction on X-ray images using special transformer networks. In 2017, I started with graph convolutional networks, and I finished my PhD this year in May 2021 in the same topic, that is graph deep learning for healthcare application. During my PhD, I focused mainly on how to deal with multiple graph scenario. It is a little bit late, but to ask, am I properly audible?
Yeah.
Okay, perfect.
That's good.
Perfect. I focused on graph heterogeneity. So basically how a graph can be different at different locations and how to deal with it and how to get optimum representation learning out of it. I also worked on graph learning. Basically, I did an internship at Imperial College London with Professor Michael Brunstein, and that's where I focused on graph deep learning. I also looked into personalized disease prediction problem using GCNs and data imputation, basically how to deal with missing values in the data set, which is a major problem in medical data sets. Currently, I'm a postdoc at camp focusing on multimodal data analysis and graph deep learning. I have, during this time, so far I have looked into cross-modal data retrieval using graph convolutional networks. That is getting back to my master thesis, but this time with GCNs. Graph classification problem, image registration using GNN transformers, also EEG signal analysis for epilepsy prediction, and also interpreting GCNs, like developing new interpretation methods in order to understand how GCN works. Okay, so this is a small team that works on graph deep learning at camp at Technical University of Munich, and I'm currently leading this team along with the medical image analysis team at the same chair. So, so far, these are a couple of publications in which I was personally involved. So these are not all of them, but some of them in which I closely worked on. Our current focus is also into prediction of ICU admission for COVID and mortality prediction, cross-modal data retrieval with missing value, protein interactions, brain signal analysis, also aiding disease prediction by interpretability methods, and also epilepsy detection. In future, we would like to focus on multimodal decision support in pathology and also looking into more validation methods for data analysis. Okay, so let us start with our first topic, I have divided the talk into two topics. The first paper is RA-GCN, that is Graph Convolutional Network for Disease Prediction Problem with Imbalanced Data. This work is mainly done by Masa Gourbani, who is supervised by Professor Nawab and myself from Technical University side, and she's also affiliated to Sharif University in Iran. So in this work, we have focused on how to deal with imbalanced data. So in the presence of class imbalance, as we all know that classifier is biased towards a major class, right? So here in the diagram, you can see that there are two classes. One, the number of points in one class are higher than the other. And the classifier conveniently draws the boundary, which actually gives a very good accuracy, 88% of accuracy. However, when we see the F1 score or ROC AUC, we see that the classifier is not working as good as it should. So how to basically deal with such a scenario, especially in the graph-based method, is the focus of this problem. So very naive way to deal with class imbalance is weighted cross entropy, right? So basically, here you have these weights, which are the BCI, and these weights are class-specific weights, and then you apply them in your cross entropy loss. So these weights are inversely proportional to the frequency of sample in the class, right? Also, they are pre-computed and they are fixed for each class, and they are not sample-specific either. What do I mean by sample-specific? Let me give an example. So here, let us say we have two classes. One is the squares and the other ones are the circles. And I want to have a classifier that classifies these two classes. You can see that the classifier will easily classify this point A. So the probability with which this point is getting classified into class 0 is 94, basically, which means that the classifier is super confident. However, the point that is closer to the classifier boundary, the classifier is no more confident. So it says that there's a 52% probability that this point is in class 0 and 48% probability that this point is in class 1. So basically, in weighted cross entropy, what we do is we give same weight to both of them, about both the point A and B, irrespective of their position in the data distribution, right? So this is where we want to focus more. Like, should that be that way? Should we not focus on B a little bit more or on A a little bit more? So towards this, we developed dynamic weighted cross entropy, as the name of this slide says. So here what we did is instead of having a fixed weight, we have a weight that is associated to each sample point I in the data set, and we try to learn these weights. And we train this particular cross entropy loss along with these weights in an adversarial manner. What do I mean by that? Is we try to maximize the value of these weights and try to minimize the cross entropy loss, which means that the value of weight should increase for the points that are getting misclassified in the previous iteration, which means specifically points like this, right? The B points here. So this was like our major contribution in our paper. So this is the proposed model where we introduce this loss. So stick with me while I walk you through this diagram. So basically, our input is a graph-based input. What do I mean by that? So there is a population level graph where each node represents either a sample or a patient or an object, depending on the application that you're trying to solve. So each node here for us is a patient, and features, they come from one of the modality from the multimodal data. So here each patient has feature vector coming from imaging data, and this graph structure is constructed at the input point itself, that is, it is pre-computed based on the other non-imaging modalities that come in the multimodal data. So basically, in this work, we have this input scenario already fixed. Now we have two different parts of our network. The upper part is classifier network and the lower part is weighing network, the group of weighing networks. What does the classifier network do? So basically it takes all the nodes as input along with the graph and tries to learn the representation for each node here. So at the end, it tries to learn the probability of class, like what is the probability that this point is in class A or class B. And basically these logics then go to the cross entropy loss at the end. from the bottom part where we have these weighing networks, right? So we have C parallel weighing networks for C classes in our data set, and which are parallel to each other, and the weights are also not shared. So how do we inject the input data to these weighing networks? Basically, we prune this graph by removing the class that do not belong to that particular branch. For example, if I'm talking about class 0, I will get rid of all the points that are not in class 0 from the input graph, and also the edges connecting them, and only take the training samples from class 0 and create this input scenario for the branch that is responsible for learning the weights of that class. So here also we use GCNs, which operate on the input features, which are duplicated from the input here, and they learn the weights at the end, which actually go in this cross entropy loss. So basically, these particular branches are responsible for learning node level weights for our dynamic weighted cross entropy loss. We also use an entropy term in order to avoid the sharp distribution of edges. What do I mean by that? Like, we do not want to have a complete focus on only a couple of points in the distribution. So in order to make the distribution a little bit smoother, we add this regularizer to our loss term. Apart from that, we also have softmax term at the end of each branch, such that the model is not biased towards any class, any major class or minor class, such that the summation of all the nodes here ends up becoming 1, and so on for the others too. All right, so this is that was our network. We applied this method to 3 different data sets. One is diabetics, one is Parkinson disease prediction, and third one is called Haberman. For diabetes data set, the classification was of 2 classes, whether the patient has diabetes or not. For PPMI, we are predicting whether the patient has Parkinson or not. And in Haberman data set, we are predicting that after the breast cancer surgery, whether the patient survived or not. So basically, these are the number of samples in each data set. You can see that in medical scenario, we do not have a data set with a very large number of samples. These are the number of features that came along with these data sets, and the number of graphs that we could construct from each of the data set. We also report the density of the graph or adjacency matrix here. And you can see that PPMI basically has this very sparse graph. Here also you can see the imbalance ratio, and the easiest data to deal with is the diabetes data compared to other two data sets. So these are the results for diabetes data set. For all the data set, actually, we compared with 5 different baselines or scenarios. One of them is MLP, that is non-graph based method. Also unweighted, where we use simple cross entropy loss. Then MLP with weighted cross entropy loss. Then a graph based method. This is standard Kif et al. GCN with unweighted cross entropy and weighted cross entropy. Then a state-of-the-art network that actually focuses on imbalance data set, and also ours. And you can see that our model outperforms all the other methods with a very good margin. One more important observation that you can see that we can see here is graph-based methods perform much better than non-graph-based methods. We achieved an improvement of 8% in terms of accuracy, 5% in terms of macro F1, and also 4% in terms of ROC-AUC. For PPMI dataset, the scenario was more or less the same. However, RA-GCN was performing better in terms of accuracy and ROC-AUC, but the macro F1 was better for RA-GCN. For Haberman dataset, again, RA-GCN was performing better in terms of accuracy and F1 score with a very good margin, but MLP unweighted ended up performing really good for ROC-AUC. We also performed an study for our proposed method. So basically here we wanted to check whether the weighting network, the way we are defining the weighting network is good or not. So the first baseline was no weighting networks. So simply GCN unweighted, then class weighting network, which is weighted cross entropy, then one sample weighting network. What do I mean by that is instead of having parallel branches, just just having one branch that actually learns weight for all the samples. Then separate sample weighting networks, but with shared parameters. And then this last one is the proposed, where we do not share the parameters and have separate parallel branches. We perform this experiment on two synthetic data sets with the sample ratio of 95:5 and 75:25. And you can see that in most of the scenario, RA-GCN, that is the proposed model, works better than all other baselines. So this, again, this is like the visualization of weights that are learned by our method. On the left-hand side, you can see Kif et al. GCN, where we used weighted cross entropy, and basically the weights were fixed for both the classes, which is the square and the circles. However, the RA-GCN is able to learn a distribution of weights throughout the entire data set. Yellow means the highest and blue means the lowest. So these are the blue points, and the classifier is able to focus more on the minor class, which basically cross entropy loss, weighted cross entropy loss also does. So which means that it incorporates the properties of that, as well as it is able to give more focus to the points that are closer to the boundaries. And you can also see that the boundary is totally shifted from this location to the upper location in order to incorporate more points from the major class and performing better. So basically, if you compare the results of both of them, you can see that compared to weighted GCN, RA-GCN ended up performing 11% better than GCN. So this was our first work. I will move on to our next paper. That is semi-supervised graph knowledge distillation for graph independent inference, that is GKD. This paper is also mainly Masa's work, and this paper was presented in Nikkei 2021 this year in October. So what is our problem definition? As I mentioned in the previous work, that the input scenario looks like this, that we have a graph and each node is basically a sample, and we want to kind of operate on these nodes and do either node classification or predict the link between them. In this work, we have mainly focused on node classification. And we want to learn kind of representations from these input features such that they can be classified into either of the classes. So let's say our node features are a matrix, n are the number of nodes and f are the number of features, and we have adjacency matrix also given for these nodes, which is of size n cross n, and we want to learn z, that is the lower dimensional feature. So our problem basically ends up becoming like this, right? Function of x and a is equal to the lower dimensional representation. And what we want to do is, what is the class of this unknown node? Okay. So what is special about our method? Because this could be done by a simple GCN or any graph-based method, right? So basically here, our method is inductive and semi-supervised. So what do I mean by that? So like in our data set here, we have very small amount of data that is labeled. So combining a small amount of labeled data with a large amount of unlabeled data during training is called unsupervised setting. So this setting comes between, is called semi-supervised setting. Semi-supervised setting comes between unsupervised learning, which is where there is no label for the training data, and the supervised learning, where we used only labeled data for training. So basically in this work, we are going to deal with very less amount of data labels. We are going to deal with very less amount of labels in our network. What do I mean by inductive? So usually in lot of GCN based methods, all the test points and training points are present during the training itself, right? So basically the graph is built between the test and the training point, and the back propagation is only done from the training points. So this setting is called transductive. So here usually there is a risk of message data leakage. So basically the test points do influence the representation learning of training points and during training. So in our method, we mainly focus on inductive learning. So basically we do not have any test samples involved during training. However, we just introduce them during the test time. So okay, so here is the input scenario if we have the test samples also during training for us. So basically we have a graph And well, let's say for test samples, you do not have a graph, right? So this is also one major important contribution of this work, that what happens if the test samples do not have a graph, or we do not have the information for building the graph for the test samples. So if we have a transductive setup for such a setting where the test samples, we cannot incorporate them into the graph. Let's say we still apply such a setup into a GCN, where these isolated nodes are the test nodes and the connected nodes are the training nodes. You can see that the training nodes, they do aggregate the information from the neighbors and do update themselves. Here we have represented it in terms of intensity, the color intensity. So you can see, for example, this point has been updated using the color of its neighbors, and so are the others. However, these isolated points where the self loop was involved are not much, they did not change much. So basically the representation did not improve, or they were not able to take the advantage of graph in learning their representation. So if I have to use their representation after the training to do the classification, their representation will be a little bit under par compared to the other points that are involved inside the graph. So basically this is our setting. So where at the training phase, we have the graph, we have very less amount of data that is labeled, and high amount of data is unlabeled. And for the test samples, we do not have the graph, and we do not also want to inject them during training. We want to bring them only up during the testing. So basically in a medical scenario also, this is an important setup. So let's say a patient comes with a multimodal data, right? So the patient has taken MRI, patient has also taken blood test and so on, but his electronic health records or the other medical history is missing. So if this graph is built by these medical history or electronic health records, basically that patient cannot be incorporated inside the graph. So if we in such a scenario, this setup is very useful. So what we want to do is we want to have a network that actually takes this input, learns a network based on this input, and then also should be able to test on test samples which do not have graph. So for this particular problem, we proposed a teacher-student network where the teacher is able to deal with input graph and the features of labeled and unlabeled node, and produce the pseudo labels for the unlabeled node. And then these nodes together with the input node are then used to train the smaller student network. So let us dive into the teacher block first. So as I said, the teacher is capable of operating on graph as well as on features of labeled and unlabeled node. So basically we have here a fully connected classifier that takes the labeled node as input, and we apply a cross entropy loss to kind of learn the labels for this unlabeled training nodes. Now, after the T1 iterations, let's say this network is fully trained and we have some labels for these unlabeled nodes, right? They are not as confident as the ground truth here, but to some extent, let's say this fully connected network was trained properly, and then we were able to get some distribution of probability for each point, right? So what we do is then we bring them in the graph setting with the input graph that was given, and initialize the node with this particular distribution for the labels, and then apply a label propagation algorithm. What is a label propagation algorithm? Basically just this. Oh, I'm so sorry about that. Is my screen properly visible now?
Yeah.
Okay, so the label propagation algorithm is basically this line here. So what we do is for each node from the unlabeled training node, we aggregate the labels from its neighbors, and then update the label for the unlabeled node. Also, we don't want to disturb the label of the labeled node, right? the node for which the label was already available. So we add this remembrance term, where this remembrance terms assures that we are not changing the label of this particular node, which was already a labeled node. After T2 iterations of this particular label propagation algorithm, we get even more confident labels for this unlabeled node set. So basically, this is how we kind of make our model a little bit more confident for these nodes. And we use these new labels as a teacher to train another network. So once we have the learned ground truth, and also the original ground truth that was available, we use this particular bigger data to train a smaller student network with less number of parameters, and the test samples are then fed into the student network, and the student network is trained using the pseudo label. So we applied this method on a byte dataset firstly, which comprises of 871 patients, and there are 2 classes. So we have to predict whether the patient has autism or not. So you can see that here we have compared our network with 5 state-of-the-art methods, and the GKD, that is the proposed method, performs the best in terms of accuracy as well as F1 as well as AUC. We also performed an experiment where the graph is available during testing phase, right? So in that case, you can see that surely if the graph is available in the testing phase, the model ends up performing better than the earlier scenario in all the cases actually. But even then our method ends up outperforming the other methods. We applied the same algorithm to another data set called tadpole data set. So here we have Alzheimer's disease progression prediction problem. So we have like 2029 cases and 2 classes. That is, we have to predict whether the patient, whether the Alzheimer has increased in the patient or not. So basically you can see in the table on the top, we have compared with the same 5 methods, and GKD ended up performing better compared to all other methods. And when the graph is present during the testing phase, the performance overall increases. However, the GKD, that is the proposed method, ends up performing better than other methods. Okay, so in conclusion, I think I am on time. So in conclusion, we have looked into 2 topics, that is RA-GCN, that is Graph Convolutional Network for Disease Prediction Problem in Imbalance Data, where basically we saw how to tackle the problem of imbalance in the data set using Graph Convolutional Networks. And second one is GKD, that is Semi-Supervised Graph Knowledge Distillation for Graph Independent Inference. That is, if graph is not available in test time, how do you deal with the scenario? So thank you so much for your attention, and happy to answer your questions. If you would like to collaborate with any of our team members, or if you want to discuss any of your project with us, please feel free to write an email to me at anis.kazi@tum.te. Thank you.
Thank you very much for the very interesting talk, Anis. So now we're going to move into the Q&A session. So please do ask your questions in the Q&A tool at the bottom, and we'll go through them. If you would like to ask the question yourselves, please raise your hand and we can unmute you and you can have a brief discussion with the speaker. So I leave it now to Fabrizio, who's going to moderate this talk.
Thank you very much, Giuseppe, and thanks, Anis, for the great presentation. Thanks very much. Right, so let's kick off with the question and Q&A session. We talked about many things. I think now I can see no questions coming. Maybe you can start from something I had on my own, maybe. So if we start from the first, let's say, paper, so RA-GCN. I think a very interesting part to me was the parameterization of the weighting network, and you also had an ablation study in which you presented how different choices may, let's say, have an impact on the results. The question I had was if you have by any chance tried with other parameterization. So I'm thinking about, for example, just standard MLP without any links between the nodes. Whether, like, why it is actually important to use a GCN in order to parameterize, the weighting network, and whether this is actually important or not, or maybe this is more important in certain scenarios or less important in others. So I think this was an interesting bit, and maybe if you can expand a little bit more on that, I think it would be very, very interesting.
Thank you so much, Fabricio, for a very nice question. Actually, I didn't have time to explain that part. I skipped that slide. So basically, yes, we did show one test on MLP, weighted and unweighted, which is non-graph-based method, right? And you can see that when you switch to graph-based methods, the increase in performance is quite significant here. Apart from this, actually, in the medical scenario, when you have multimodal data, so basically, it is a very good choice to kind of focus on different modalities separately. For example, let's say I have imaging features coming from whatever MRI modality, and then I have non-imaging information, which is like hardly 10 or 20 features. However, these 10 or 20 features are kind of important compared to all the big data feature vector from imaging modality. If I concatenate them together, the importance of these 4 or 5 features is lost. So it's better to kind of incorporate their information in terms of graph. And in our other publications, actually publications from 2017 and 18, this has been our focus to find out whether analyzing multimodal data using GCNs is a better choice compared to non-graph based methods or not. And there we found out that actually the graph based methods end up mimicking the role of clinical experts. So why do I say this? So basically, when a patient comes to the doctor already looking at these clinical records and non-imaging data already has a bias in the mind to like he or she knows what to expect out of medical imaging data. So such a setting is incorporated in graph if we use GCNs. So yeah, I mean, for multimodal data analysis, at least in medical scenario, GCNs are a very good choice, and we also show that here in terms of results. I hope that answered your question.
Yes, thank you. Maybe a quick follow-up on this. I think in one of the papers, probably this one actually, you mentioned the fact that it may also help with overfitting. So to use maybe modalities to construct a graph rather than simply use modalities as plain features, and this may help maybe with the generalization ability of the network itself. Was wondering if you had any more detailed maybe intuition about this, or if this has also a role in terms of generalization ability outside of maybe training distribution?
Yes, again, a very good question. So basically, this it is from this paper itself. So here we do add this entropy term for the same reason, such that the model does not overfit on particular points in the data set. And apart from that, here basically we add like a softmax function in order to limit the value of the weights that are getting learned for any particular class. So basically that helps us avoid the overfitting. So I was mentioning that that softmax function along with the regularizer helps the model not to be biased towards any class. So yes, I think this was the explanation written in the paper.
Thanks. So I think we have a few questions. Maybe you can club them together. They are all about how one may construct the network. What's the meaning of the network in this kind of medical problems? What's the right way to use it, whether to use it at all, and maybe what's the role of the network in solving this task? I think this will allow us to maybe take a step back and redescribe just a little bit the context of why this is important and how we constructed the network and what's the role of the network in this kind of problems.
I see. By network, do you mean the graph or?
Yes, sorry, I mean the graph. Yes.
Okay. All right. So, okay, very, very good question again. So, thank you so much for this question. So, basically, here, The graph construction choice, I will answer it in parts. So first question was about how to construct the network, right? And which is the right way to construct the network and so on. So how we have done it in this particular case, I can tell you that first, and I can also give a bit insights about what we can do apart from that. So here in this network, we followed the state-of-the-art method. So what we did, let us say we have age as one of the factor, then gender as one of the factor, and a blood test as one of the factor. So based on a threshold, such as for age graph, what we did is that if two people or two patients have age difference less than 2 years, this threshold of course is determined experimentally, and we have followed the previous paper to kind of use this threshold. We connect the two patients, otherwise we don't. So we get an age graph like that. For gender, it is straightforward, whether the gender is same. If the gender is same, you connect, otherwise you don't connect. For blood, also blood report value, also the same. We used a particular threshold that is empirically defined by the state-of-the-art to kind of create the graph. Once we have these three graphs, we sum them up and take the average graph out of it. So that's how the graph is defined here. To be honest, that is not the focus of this paper, but in reality, that is not the optimal way to define a graph. So we do have ablation study in our paper where we have used, I think I have a slide for that in my backup slides, where we have looked into different graph construction techniques and have reported the results. Let me see. Here. So basically here we have seen different graph constructor methods in order to build our graph. And these were actually referred by the reviewers of the paper. So one of them is one of our previous paper, which is dynamic, one of our, which is DGM, that is graph learning module. So basically there what we do is we learn a threshold in order to threshold our graph. So basically you can learn that graph. Another method is from Professor Bronstein, that is dynamic graph CNN. There you actually construct a KNN graph on fly. So basically if your representation is changing in every iteration, your graph also changes in every iteration. So the graph learning module that I was talking about is differentiable graph learning module. So basically there, the graph learning module itself is differentiable because we are simply getting a fully connected graph using Euclidean distance between the features, and then thresholding them and learning the threshold as well. So yes, in a nutshell, constructing the graph based on threshold manually is not an optimal choice. A better way would be to either build a graph on fly using KNN or learn a graph using DGM. I think this was one part. Was there anything else that is left?
I think this is already small, yeah, very enlightening, because, you know, one is typically used to think of a graph when you talk about social networks and or this kind of domains where edges are very intuitive. So you either you follow another user or you don't, and this will basically give you a graph of shells basically. But in case of medical data, then as you explained, you have to kind of construct the graph your own, and your own graph. And I think throughout both the two papers you presented, it emerged as the fact that the graph itself, so using a graph rather than not using a graph at all, this may also have this may be advantages in general. So yeah.
Just I wanted to add one more point.
Sure.
So basically here I wanted to comment on these numbers. So you can see that when we were using a particular graph constructor method here, the performance was not as optimal as when we had an input graph. So basically this was also one observation that we had in our experiments previously, that the optimization task becomes a little bit difficult if you are kind of optimizing for graph as well as for the task. So if you're performing, if you're looking into graph learning, just wanted to mention that, keep it in mind that this is like a double optimization problem.
Right. Thanks, Anis. We have another question which is related, so maybe we can cover that and then move maybe to the other paper or any other question. So Edward in particular is asking, what's the intuition for why creating a graph from similar features and then using GCN? Why this works better than just using features and then an MLP it's without constructing a graph and then using a GCN. So what's the intuition behind? I think it's related to signal processing on graphs and denoising, I suppose. So you want to maybe mention a few things on this?
Okay, thank you so much for the question. So actually, this is related to the question that you asked before, right, Fabricio? Like, why not non-graph based methods? So maybe I can explain in a different way. So basically, at least in a medical scenario, GCNs end up mimicking the clinical situation better than a non-graph based method. So giving an example of that, as I was also earlier mentioning, that if a patient comes to the doctor already has a bias towards the patient, looking at the age, looking at the gender, looking at some other blood reports, and looking at some previous reports, for example. So these bias is introduced through graph. So what do I mean by that? So if I create a graph based on age, I connect all the patients that are, let's say a patient, the test patient is 80 years old. I'm connecting that patient to all the other patients who are either 82 or less, or 78 or more. So basically the representation for that patient will be learned only based on this subset, because they are its neighbors, right? Also, it depends on the filter size that you're applying, but let's say you're just looking into first hop or second hop neighbor. So in that case, you're only using the population which is very much similar to that test sample. This does not happen in case of non-graph based method. Each sample is considered as independent sample, and overall the network parameters actually ends up deciding how we can change the features of the input image, right? So basically this bias of subcategorizing even within the population is done via GCN, and this is very much helpful in medical scenarios, at least, because their doctors also do the same. So if the patient is 80 years old, yeah, then the probability of Alzheimer's is a little bit more compared to someone who is 40. So this is why graph is a better choice. Also for multimodal data analysis, as I mentioned before, that concatenating very less number of features to a high dimensional imaging feature is not a great idea. We do have a couple of experiments in our paper. Maybe I can quickly tell you. Maybe I can share the set of papers where we have done this experiment. So basically in these papers, we have validated this, that GCNs do perform better compared to non-graph based methods. So which is why it was one of our general choice to go forward with.
Thank you very much, Anis. That's great. Maybe I have a related question somehow that can maybe link us to the second work a little bit more. That is, well, you mentioned also earlier that many times you have more than one modality, so you have multiple modalities. So, and maybe the optimal, or at least a reasonable choice would be to use some of them as just features or nodes, some of them to define a graph. And one of the ways you may define a graph is to basically consider different thresholds, estimate in different ways for each of the modalities you consider to create a graph, and then you kind of consider the union of all these graphs. That is, you kind of sum the adjustments and matches, I suppose. So the question was, like, do you think it might be sensible to keep, let's say, some form of edge features in a way to retain the information that there were many modalities together that formed an overall connectivity, an overall topology between the patients? So would it make sense to consider maybe to retain features on the edges, conveying the information about the modality that has been used to create this topology, and then maybe use a more sophisticated GCN method accounting for edge features as well? Standard GCNs, for example, GCN, they don't typically consider edge features, but I was thinking maybe this would be done with a more sophisticated GNN. Maybe this information may be useful. Do you think this might be a reasonable choice at all, or what are your thoughts about it?
That totally is a very good idea. Actually, we are also looking into this direction. So rather than selecting the features for ourselves, we plan to have a mask that kind of learns which features are important for the graph construction. So far we have not looked into like exactly edge features, but however, in one of our paper, I have a backup slide for that as well. Let me see if I can open it quickly. So this particular paper, right? So basically, in this paper, we do not choose what features should go for graph construction and what should not. So basically, we give all the features that we have to this parametric function f of theta, which basically is an MLP for us for now. And this network ends up learning the embedding that gives us then the optimal graph. So basically, here we get rid of the problem that how do we choose the features for graph construction, what should be the threshold for that, and also apart from that, how exactly this graph has to be constructed also. So basically this network takes care of all three of them in itself while learning. So that's a very good comment and question at the same time. So looking into the edge features is actually a very good idea as well. Mainly in order to kind of learn the attention for each of the let's say feature that we want to use for graph construction.
Thanks, Anis. I think also a kind of attention-based model may give us some insights on the relative importance of some modalities with respect to others, if one would like to maybe peek into the attention weights. So probably this also may lead to more interpretable modeling, do you think?
Well, towards that also we have another work. So maybe I have a slide for that as well. So basically this one. So here, this is the work that we recently did with one of our students, Sorush. So here we did the exact same thing that you're mentioning, Fabricio. So we initialized a mask. And this mask is then the initialization could be anything. Here we have initialized it with the Gaussian initialization, and we apply a sigmoid on top of this. So basically this part is learnable. So this part ends up getting the values of these masks changed to 0 or 1 or anything in between, depending on how important the corresponding feature is. So the size of the mask is D, which is exactly same as the number of features that we have as input. And we have also defined a loss function that basically operates in an adversarial manner in order to make this mask confident to tell us which feature is important for a better performance of the model, and which feature in short is also important for that task at hand. So in this particular paper, actually we ended up also doing some knowledge discovery. We just found out we took the features that our model gave more attention to and compared them to the clinical papers, and found out that there was a high correlation between the features that were found by the model and the features that are given as important in the clinical paper. So which was quite surprising for us as well. So yeah, that's a very good comment again, but yeah, we already worked on it.
Great. Well, maybe if you want to stick for a while on multimodality and your second work you presented, yeah. I think, yeah, there was something I believe it was interesting, that is the fact that you actually use a label propagation algorithm. And I think in the paper you also compare with standard GNN algorithms, so GNN baselines. And I think this is interesting because, you know, to some extent, over the past, I would say maybe 4 years, GNNs are, you know, they have really taken over. And to some extent, you know, label propagation has kind of started to be forgotten. Whereas of course, in some application, this algorithm may still have a very, very high relevance. So I found it quite peculiar, but also interesting at the same time to notice that you decide to actually go with a standard label propagation algorithm on top of the predictions. And also judging from the results, it seems like that this is working much better than the standard GNNs, right? So I was wondering if you have any comments on this. Like, do you think label propagate, like, because one may ask, when do I have to use just label propagation rather than a standard GNN if I want to somehow make use of the connectivity I have, but in a way that is really the best for the problem at hand. And I think this is also this might be also related to the fact that at least a few works in the literature, they seem to actually try to combine the two. So to do kind of message passing, considering not only node features, but also labels. So in a sense, this is kind of trying to use both the two algorithms at the same time or fuse them together. So do you have an idea or any comment you would like to make on when label propagation is better than GNNs, or when GNNs are actually better, and when it might be interesting to combine the two? What's your idea about this?
Again, a very nice question. So basically here, here for the label propagation algorithm, we are using the output labels that come from this network, right? In case of GNNs, we will have to deal with the input features in order to change them, because we don't have labels for the unlabeled data. So intuitively, I would say that it will be difficult to optimize this problem with GCN, because in case of, let's say I replace this fully connected network with the GCN, so I have to train the entire model only on labeled data and not use these labels in order to learn or make the label more confident. So in that case, the labels that we get out of this label propagation algorithm will be much better and more confident compared to the previous case, right? Because here what we do is we get these output labels, we apply the label propagation on the output labels, not on the input features. So that is the major difference, right? So basically, which is why I think having a label propagation algorithm separately here makes much more sense than using a conventional GCN right away to learn the labels. And combining the two, I'm not sure if I can comment on that, because for example, we have an input graph here. Yes, we can have an input graph scenario exactly as this, but initialized with input feature, and then have a GCN, and then learn these labels the way we have learned with fully connected networks, and then apply a label propagation algorithm. Maybe could work better, because if you have a GCN instead of fully connected network, then the chances of the representation, learning of these representation here would be better representation would be more. So basically with GCNs, it will take help of all the graph information, that is neighbors, as well as the nodes which are labeled, in order to learn the representation, which I assume would be better than simply using a fully connected network. So yes, combination would be much better, yes, but I personally would not replace fully connected network with a GCN to learn the labels here.
Thanks, Anis. Yeah, maybe on this line, I think yeah, in general, like there's maybe an interesting, also maybe some more like subtle detail, that is when there is connectivity between a node and its neighbors, and this connectivity, whether this adjacency is also correlated to sharing the same label or not. And sometimes, especially when you have missing edges, you have missing connectivity, you don't actually observe modalities that you can draw the graph from. So sometimes this makes your nodes to maybe be connected with predominantly with other nodes not sharing the same label. And it seems like this might also be, I would say, detrimental for GCNs. So this leads me to maybe wonder if there are particular scenarios where you believe graph approaches might not necessarily be the right choice. For example, there are, I don't know, special medical applications where you would expect the graph to encode some form of heterophily, maybe, or you have labels not really correlated to the topology, and maybe GCNs do not really represent a good choice. Have you ever had any experience with this kind of more peculiar maybe applications or more challenging applications maybe for standard graph neural networks? Or do you think GNS may just work well in any case as for medical applications? What's your take on this?
Thank you for this question as well. So basically, yes, there are scenarios where GCN surely might not end up working well. So it's not like GCNs are like a super models that will work on anything everywhere. So in the past, I'm talking from the medical domain. So basically, we had one data set that is Abide, which actually we have used also in one of the papers here. So there we were trying hard to make GCNs work better than other methods, non-graph based methods. And after doing everything, hyperparameter tuning, changing the network, we tried everything, but the GCNs couldn't work. They couldn't perform good. So we dived a little bit deeper into why that's so. So we saw the input embedding, like the input feature embedding itself. And the input feature embedding, the points of different classes were so overlapping to each other. Like it was such a difficult, already a difficult problem to kind of classify the two. Having a graph on top of such a scenario was making it even more difficult, because let's say I have two different clusters of two classes, they were overlapping on each other, and then I was creating a graph on that. So the representation that was getting learned for any point in that particular setting was getting learned randomly from any of the two classes. So basically the representation that was getting learned was like not optimal in that setting. I can point out to one more problem, that graph construction here is a very crucial point. So if you already, like, it's not like you can take whatever data you have and just construct the graph and it will end up working better. So in case your graph also is such that it is bringing the points that are not in favor of optimizing your task together, then the GCNs will not work there. One more point I had in mind, but I forgot. So, yes, but in short, GCNs, it's not like they will work everywhere. Like you have to choose wisely depending on your task, depending on your input data size, depending on your input feature embedding. And yes, I wanted to say that what we did is we kind of computed correlation between a couple of input features and the labels. And we saw that there were four or five features that were highly correlated to the labels. So just for fun, we created a graph out of these features and performed our classification task, and it ended up outperforming everything. So which means that the graph construction, how much the graph itself can segregate the points is really also important in this case.
Thanks, Anis. Maybe quickly on this, there was a question from Fabio, which I guess might be related. It is, well, you were talking about other parameters, and of course, one typical other parameter is, the depth of a GCN, right? So that in turn basically means how many message passing iterations you perform. And you're mentioning the importance of the, for example, of the way you construct the graph, and of course the way you construct the graph, this may have an impact on the diameter of the network and the size of the graph, and so the average, for example, distance between two nodes. So I guess these are all factors which might be, let's say, related to how the network should be, like how deep the network should be, right? So do you think like there's a golden standard or a golden rule or any rule of thumbs or anything like this that maybe you would suggest, or do you think the depth is simply yet another parameter to tune? What's your experience on this kind of yeah?
You mean like how to decide the model architecture?
Yes, I mean, like if you've observed, for example, that the depth of the network, that is the number of stacked message passing layers, if this has a particular impact in general in this kind of applications, and if so, how one might choose it. one thing maybe I can mention is, in my experience, there is an interesting emerging research direction in GNS that is related to studying when these networks will perform over-smoothing, for example. That is, if you kind of keep applying layers and layers and you go as deep as you want, as you can also, then at some point you may have that the features may get averaged out altogether, and then maybe you may lose, for example, important signals in your input features. Is this something that you have ever experienced in this kind of medical applications? Or do you think, like, was the typical depth of your network? Yeah, if you have some comments on this, I think, yeah, this would be very helpful. Yeah.
Absolutely. Thank you so much again for a very nice question. So yes, it is difficult to define the depth of the network, especially how many layers you should have in your graph convolutional network, because by adding the layer, you are kind of adding the aggregation from the farther points from that point itself. So one example, let's say I have a Kif et al. Network, and my value, I choose only one hop neighbor in my graph convolution. So if I attach another similar graph convolutional layer, then the output of graph convolutional layer is basically aggregating the 2 hop neighbors. And if I add another, then it's 3 hop and so on. So what happens if you have a very deep network is that at the end, you are, for any point, you're kind of considering almost all the points that are there in the in at least in the surrounding of that point, right? So as you said, that the features gets averaged out, and you get, for all the points, you get the same features, right? So in medical domain, actually, this is a very crucial problem, because first of all, the datasets are small. As I showed that we had like 700, 500 points in our data set. So in this particular case, it is very important to kind of not have a very deep network, because the averaging problem ends up happening in that case. Apart from that, it also is related to the density of each, like the degree distribution of that graph, right? So basically, if you have a lot of points connected to a lot of points, then yeah, in one layer itself, it will get averaged out. So towards this, actually, was one work about graph heterogeneity, right? Like how exactly is heterogeneous your graph is, and how to learn optimal representations in such a scenario is one work that we worked on. I hope I have slides for that as well. Okay, I think that's a very old work, so I don't have slides for that paper. So, but that paper is called Inception Gcn. So basically, we have mimicked the Inception module from GoogleNet. It is here, and not very pretty, but somehow. So basically, here what we did is, in the input graph, you can see that the graph is super heterogeneous. At certain location, it is compact, and at certain location, it is more sparse. So what we did is we applied filters with different receptive field sizes, and then used 2 aggregator methods here. So one was concatenation, the second one was max pooling, and then we found out that way the representations for each node was learned better. Because, for example, in this scenario, let's say the optimal choice of receptive field is 2. Let's say K value of K should be 2. However, that's not optimal for this one. So this model was able to, help the input features from different locations to kind of, it acted like a gate, like gates, So for this location, this particular model was good. For sparser one, probably the higher one was better, and so on. So we ended up learning better representation in this case. We also performed experiment by augmenting such inception modules more and more. But in our cases, we found out that after certain limit, the accuracy does not increases at all. So it's like a exponential invert exponential graph. So simply we increase the parameters, but there is no benefit of that. So there is one particular combination, or let's say one particular point where you find out that, okay, the number of parameters needs to be only these many, and then I get the optimal results. So in this paper, we did perform that experiment also by adding more and more value of K and more layers also. So yeah, this was our observation.
Thanks very much, Anis. I think with this we can wrap up the session. So I'll let Giuseppe make the conclusions.
Right. Yeah, we just ran a bit out of time, but Thank you very much for the very interesting talk, the very good discussion, both Anis and Fabrizio. Thank everyone for attending and for the very interesting questions. As usual, the talk is going to be uploaded to our YouTube channel, so please look up for the London Machine Learning Meetup on YouTube and subscribe to get all the new videos. And yeah, thank you very much for joining. See you next week. Bye-bye.
Thank you so much for joining. Bye.
Bye, everyone.